Hello everyone. In this AV we are going to talk about chapter 17, that is flow of liquids. So let's understand that what we can call it as an ideal liquid. For a liquid to be an ideal liquid, it should have zero compressibility. What do we mean by zero compressibility? It simply means that when the liquid is pressed, then there should be no change in its volume. That means when we say no change in its volume, we also mean no change in its density, that is rho. Now the second point is point number 2. An ideal liquid should have zero viscosity. That means, what is viscosity? We know that whenever a liquid flows, it flows in layers. So there will be a viscous force, or we can say a tangential frictional force, which will oppose the relative motion between the layers, and that force is known as viscous force. So an ideal liquid should have zero viscosity. So in actual practice, what happens is there is some viscosity always present in all the liquids and gases. Maybe it's less in gases but comparatively larger in liquids. Now we have two types of flow. The first type of flow is laminar flow, or also known as streamline flow. What do we mean by it? We simply mean that when a liquid is flowing, all the particles of the liquid will follow the same path and they will pass through the same point as the preceding particle. So the flow is said to be streamlined and the path is called as streamline, or the streamline flow is also known as laminar flow. So when all the particles they pass from the same point and follow the same path, then the flow is said to be streamline flow. This generally occurs when you have a liquid flowing through the tube. The streamline flow or the laminar flow occurs only when the velocity of flow of liquid is below a certain value. That value is known as critical velocity, which is denoted as Vc. So this Vc has got the abbreviation, the full form as critical velocity. When the velocity of flow exceeds this value, that is critical velocity, then the flow of the liquid will no longer be streamlined and it would go into the second type, that is the turbulent flow. So before we define turbulent flow, let's understand this critical velocity also. Now there was a scientist called Reynolds. So he proved that the critical velocity for a liquid which is flowing in a tube would be given as, the critical velocity is k eta upon rho d, where Vc is the critical velocity, k is a constant which is known as Reynolds number, as he was the scientist who came up with this, and eta is the viscosity of the liquid, rho is the density, and d is the diameter of the tube in which the liquid is flowing. Now when this K, that is the Reynolds number value, is less than 2000, then we have streamlined or laminar flow. If K is somewhat between 1000 to 3000, 1000 to 3000, then the flow is unstable, and when the value of K is greater than 3000, then the flow will be turbulent, which is the next type of flow. What is a turbulent flow? Turbulent flow is opposite of streamline. In streamline flow, all the particles, they follow the same path and they pass through the same point where the preceding particle has passed through. But in turbulent flow, the particle of a liquid will follow independent paths, and the mixing of two or more layers can take place. The layers can mix and we will have a mixture also in between the layers. So what happens here is the velocity gradient Vc is not constant for a turbulent flow. Now if we have a liquid flowing in streamline motion, so the layers will not mix, and in this case what happens is the layer which is at the top has got maximum velocity. The next layer has got slightly less velocity. The next layer has got lesser velocity, and as we reach the plane, the layer is at rest. Now what happens is, as we are going up, what we see is the velocity is continuously increasing. Now here, if we take this layer and this layer, let's say A and B, so A is moving comparatively slower than the layer B. Because of this difference in the velocity, now this layer, that is layer A, will try to retard the motion of layer B, and layer B, this layer will try to retard the motion of this. Now this is what we call as viscosity. Now this is viscosity. Viscosity. It is the property of the liquid by the virtue of which it opposes the relative motion between the adjacent layers of the liquid. Now that is why we find that if you take a glass of water and you stir it, once you leave it, then the water comes to rest. That is because of viscosity. Also, when we walk in air, we tend to walk faster in air, but if we try walking on water, then it is comparatively slower because the viscosity of air is very small, but water has got comparatively larger viscosity. And also we have the cloud particles which appear to us that they are floating, but actually what happens is they are falling down very slowly because of the viscosity of air. So now we go back to this case. Here we have the plane, and suppose we have two layers of liquid. This is the topmost layer and it's flowing with the maximum velocity, and this is the layer next to the topmost layer which is flowing at comparatively slower velocity than the topmost layer, and we assume that this distance from the bottom is z. The distance between these two is nothing but delta z. Then, and this has got a larger velocity. Now, if we find the change in velocity, that is, let's say that this is Vx plus delta Vx and this is Vx. So this layer, the lower layer is moving with the velocity Vx and the topmost layer is moving with a slightly greater velocity, that is Vx plus delta Vx. So if we find the ratio of change in velocity by the perpendicular distance between them, that is delta z. So this entity is known as velocity gradient. Now this is what we were talking about, that velocity gradient is constant for streamline flow and it is not constant for turbulent flow. Now, according to Newton, the viscous force acting between these two layers of liquid which is flowing in streamline motion, it depends on two factors. Firstly, this viscous force is dependent on area and it is directly proportional to the area of contact. Next, this viscous force is directly proportional to the velocity gradient. What is velocity gradient? The change in velocity upon the perpendicular distance between the layers. Now if we combine these two, we have the force or the viscous force is directly proportional to A delta Vx upon delta Z. Now if I have to remove this constant of proportionality and bring in equal to sign, then I have to bring in a constant, and that constant in this case is eta. A delta Vx delta Z. Here we write plus minus. We give both plus and minus. Now this plus and minus sign indicates that the force between the two layers is a mutual interaction force. They are both interacting with each other. Now this eta is known as the coefficient of viscosity. Coefficient of viscosity. How do we define it? We make all these entities, that is A, Vx and Z, as unity. If we make it as unity, we assume that they are 1 meter apart and the velocity, change in velocity is 1 meter per second and the area is also 1 meter square. Then in that case, what will happen is the viscous force will be equal to plus minus, we will have to interchange the sign, eta, that is the coefficient of viscosity, is equal to plus minus F. So we define it as the coefficient of viscosity of a liquid is the viscous force per coefficient of viscosity is the viscous force per unit area of contact between two layers having unit velocity gradient between them. So we have assumed, to define the coefficient of viscosity, we have assumed that the area, contact area, is unity and the velocity of gradient is also 1. So in that case, the coefficient of viscosity is equal to the viscous force between the two layers. Now the SI unit for this coefficient of viscosity is kg per meter per second, and the dimension is ml minus 1 t minus 1. So this is the dimension, and the SI unit is kg per meter per second. And also we have to keep in mind that temperature also affects viscosity. If the temperature increases, then the viscosity of the liquids will decrease. Temperature increases, viscosity of the liquid decreases, and it will become 0 at the boiling temperature. But this is for liquid. But for gases, if temperature increases, then viscosity also increases. This is the condition for gas. Now if we have a liquid body and a ball is gently dropped in that liquid, what happens is, initially the layer of water, the velocity of the ball will go on increasing, and the layer of water with which the ball comes in contact will have the same velocity as the velocity of the ball, but the other layers are at rest. So as a result of the motion of the ball, there is a relative motion between the adjacent layers of the water, and because of that relative velocity, a viscous force is developed in water, and that viscous force will oppose the motion of this ball. Now the magnitude of that force will go on increasing with the increasing velocity of the ball, and there will be a time or a point when the opposing viscous force will be equal to the force which is driving the ball downwards. So the net force on the ball is 0, and the ball attains a constant velocity, and that constant velocity is nothing but the terminal velocity that we have discussed earlier also. Now Stokes gave a formula to calculate the viscous force which this ball is going to experience, and this is known as Stokes Law. He showed that if we have a small sphere of radius, let's say that the radius of this sphere is r, and it's moving with a terminal velocity, and that terminal velocity is v in a liquid or a gas, then the force which is acting on the sphere, or the viscous force that is acting on the sphere, is given as 6 pi eta r v, where 6 and pi are constant. Eta, as we have discussed, is the coefficient of viscosity, and r is the radius of the sphere, and v is the critical velocity or the terminal velocity. Now the dimension we have already discussed for eta, that is ml minus 1 t minus 1, and this terminal velocity v is calculated as, we have two forces which are acting on this sphere. One is the effective force which is acting downwards, and the other one is the upthrust of the liquid, or the viscous force which is acting upward. So we have the terminal velocity, which is calculated as, the formula is 29 r cube 2 upon 9, then r cube rho minus sigma multiplied by the acceleration due to gravity upon coefficient of the viscosity. Now here r is the radius of the sphere or the ball which is falling in the liquid, rho is the density of the ball, and sigma is the density of the liquid or gas in which this sphere or the ball is falling in. G is the acceleration due to gravity, and eta is the coefficient of viscosity. Now from this formula it's clear that the terminal velocity is directly proportional to square of the radius of the sphere of the ball which is falling in the liquid. We find the application of the Stokes Law or Stokes Theorem in parachute. When a soldier with a parachute jumps from a flying aeroplane, he descends very slowly in air. In the beginning, the soldier falls with gravity, acceleration due to gravity, but soon the acceleration goes on decreasing till the parachute is fully or completely opened. So in the beginning, the speed of the falling soldier increases rapidly, and then it is very slow. Because of the viscosity of the air, the acceleration of the soldier at one point becomes 0, and the soldier then falls with a constant terminal speed. So if we draw a graph between the speed and time, then initially it goes on increasing, and then finally it becomes constant, which is nothing but this point is terminal speed or terminal velocity. Another application of this Stokes law is in the calculation of the velocity of raindrops. As we have seen that the terminal speed or terminal velocity is directly proportional to the square of the sphere. So for calculating the raindrops, size of the raindrops, or the velocity of the raindrops, this r would mean the radius of that raindrop. That's all in this AV. The remaining part of the chapter would be discussed in the next AV. Thank you.